Okay, so today we are going to start chapter 5. So we'll talk about special random variables. So I don't know about all of you, but I'm thoroughly bored with these Bernoulli and uniform examples. So I think it's high time we used all the machinery that we have to understand other random variables. Okay. So let me quickly finish the Bernoulli random variable. Okay, so I should say first we will first discuss discrete families. So the first one we have discussed any number of times, and I don't want to spend too much time on it except to define it again or recall it rather. So let P belong to closed 0, 1. Then Bernoulli P Bernoulli random variable with parameter P denoted by P has PMF. So P of 0 is 1 minus P and P of 1 is P. So as I said, you think of this as success failure or coin tosses or whatever you like. And this is useful, as I told you, when talking about indicators. Okay, so we have already seen that the expectation of x is p, and the variance of x is 1 minus p, and the moment generating function is 1 minus p plus p e to the t. Right. So we have seen these computations, and if you like, you can go and revisit them. But that's all I'm going to say about this. I've already spent enough time on this simplest and maybe too easy an example.
Sir,
Yes.
so is it P into 1 minus P, the variance?
Sorry. Yes, of course. I said it, but I forgot to think. Yeah. Thanks, Anirudh. Okay, so this is the first and maybe silliest example, but it is useful, as I said. Okay, so the next is more interesting, and I have given you a flavor of it in one of the quizzes. So let again P be close 0, 1 and n be a non-negative integer. Okay, so these are our fixed parameters for the next important family. So let x1 to xn be IID Bernoulli P random variables. Okay, so I remember what IID is. IID means independent and identically distributed, and I'm also telling you what the distribution is. So I could have just said independent Bernoulli P random variables. Okay, then set x to be their sum. Then x is a binomial random variable, and you will see why in a second. With parameters NP. So it's common to take n to be the first parameter. So it's an ordered tuple. So n is the first parameter, which is the number, and p is this parameter, which is the same p as the Bernoulli p. Okay. All right. So what is the PMF of this? Okay. So first, okay. So let me ask you, where does X live? What possible values can X take? Yes.
So any value from 0 to n.
Yeah, well, any integer value. Yes, that's right. Yeah. So it can take any integer value from 0 to n, because each of these xi's are 0, 1. So you can get all 0 with, I mean, you can get 0 if all of these are 0, you can get n if all of these are 1. And for any integer I in between, you can get it if the first I are 1s and the last n minus I are 0s, for example. Okay. So this is a discrete random variable. It takes so many values. Okay, so now I guess the hint is in the name, but let's compute, let us see what the PMF is going to be. So what is the probability of X equal to I? The PMF P of I, which is the probability that X equal to I. Well, how can X be equal to I? So you have n possibilities of having 0 or 1, and if the sum has to be I, then exactly I of them should take value 1, and n minus I have to take value 0. So that means you have to have p to the I 1 minus p to the n minus I, right? So I of them should take 1, which happens with probability p, and n minus 1 should take value 0, which happens with probability 1 minus p. But how many such possibilities are there?
So n choose I.
That's right. So again, this is something you know, and this is why it's called the binomial. Right? So this is, I remind you, this is n factorial by I factorial n minus I. And I remind you that 0 factorial is 1, like I mentioned. Okay? Any doubts about this? I mean, so if you're not comfortable with, I mean, so why do you get n choose I? Because you have to choose I of these n guys to assign 1. And that's exactly n choose I. Okay. So this is from high school. Okay. So now let's see what are its important parameters. So let's compute the expectation. What is expectation of X? This is, you know, from the way we have defined it to be the sum of Bernoulli's. This is the sum of I equal 1 to n expectation of xi. So here I am not even assuming independence, just this because it's a sum and linearity of expectation. So this is, each of them has p, so I equal to 1 to n p, and so p is independent of I, so this is just np. Oh damn. Okay, sorry. So I wanted to show you simulations. Okay, so let's backtrack. We are still on Bernoulli. Okay, so now okay, so I have coded this in Mathematica. So what I am doing now is generating independent Bernoulli random variables with parameter p equals 0.3. Okay, if you like, I can take any other p that you are comfortable with. So here are, so you know, so, and I have 10,000 samples of this. Okay. So here are these numbers. I don't know if you can appreciate these numbers in any way. I cannot. So so what I'm going to do is I'm going to count how many ones there are in this and divide by 10 to the 4th, that is or which is 10,000. So that's precisely the average of these numbers. Okay, and so I generated a fresh sample. So I have this is the number, and you know, when you divide, when you write it in decimals, you get 0.3014, and this is close enough to 0.3, the number that I started. Okay.
Excuse me, sir.
Yes.
Sir, but isn't the algorithm which is generating these random numbers itself biased? So how do we, how are we guaranteed that that the probability will tend to the theoretical probability?
No, it's not. Well, yes, it's well. But what do you mean biased? I mean, so yeah. So as I said, maybe I said this earlier. So on a computer, you cannot generate truly random numbers, but you have what are called pseudo-random numbers. And these pseudo, I mean, people have worked a lot on improving the algorithms for generating pseudo-random numbers. So for you know, in many packages, these are well-developed algorithms, and they give answers to fairly good degree. I mean, again, nothing is perfect, but you get with fairly high accuracy, you get the things. So if you want, we can test it again. You know, I generate another 10,000 Bernoulli 0.3 random variables. If you like, I change this. Okay, so let me change this. Maybe I like make it e to the minus 1. Okay, and so I get this, and if I do what is e to the minus 1, you know, it's close enough, right? And if you like, I can make it a million. And now I should change this also. Okay, so again here it's maybe slightly better. Okay, you know, so people have tested these algorithms fairly well, and there is a way to simulate from any distribution, which I will maybe tell you at some point. Okay. So any questions about this? So I'm sorry, I forgot to talk about this. I should have discussed this before going on to binomial, but right now, but I'm just simulating Bernoulli random variables. Okay, is that clear? Okay. So let me maybe go back to the binomial example. Right. So here is the expectation. So as I said, it's NP, and let's compute the variance as well. So variance of x is variance of x1 plus up to xn. And now I have to use that they are independent. So by independence, this is the sum I equal to 1 to n of variance of xi by independence. And this is sum I equal to 1 to n. Each of these has variance p1 minus p, as we said. So the variance is np1. Okay, so this says that if you simulate, I mean, if you have a binomial NP random variable, you will have a spread. So the mean will be n times p, and the spread will be of the order of np1. Okay, and the last thing I'll do is again do the moment generating function, compute the moment generating function. So I think I said GF. So phi of t, phi of t So we have seen that the moment generating function of a sum of independent random variables is the product. Okay, so phi of t is 1 minus p plus p e to the t raised to the n. So it's product of okay, maybe I'll write it in 2 steps. So this is phi x1 of t up to phi xn of t. So product of independent moment generating functions. Okay, so again you get a fairly simple formula, and now you can use this to compute higher moments, for example. Right? So okay, so now let me show you simulations for this. Okay, so now here are my parameters. So I'm simulating a binomial NP random variable where n is 20 and p is 0.8. Okay, and again I'm taking 10,000 samples. So now these will look between 0 and 20. So they look again, just staring at these numbers might not particularly help. So let's compute the mean. Okay, so you see the mean is very close to 16, and what is NP? N is 20 and P is 0.8, so N times P is exactly 16. Right? So it works to very good accuracy. Now let's compute the variance. Okay, so to compute the variance, let me go back to lecture where we discussed the third lecture where we discussed the variance of a sample of data. Okay, so the sample variance was the sum of xi minus x bar squared, where x bar was the sample mean, and in our example this is the sample mean, which I am calling mu. Okay, so I take the sums of squares of xi minus x bars and I divide by n minus 1. Okay, and we will see a connection to this. Okay, by n minus 1, as I promised. Okay, so I am computing the variance. So I am taking the sum of these ith data points minus mu, the sample mean, whole squared, and I am dividing by n minus 1, and I am okay. So let me do this afresh, and I get 3.19 roughly. And if I do np times 1 minus p, I get 3.2. Okay, so this works quite well. Okay, and lastly, let me show you the PMF. So of this, let me compare the PMF of this binomial distribution and compare it with the histogram of this data. So let me show you what I mean. So these rectangles represent the histogram that we have seen already earlier when we were talking about data, and we have so the Mathematica has this functionality where it reduces the height of this histogram, so scales the height of the histogram so that the area under this histogram is 1. And so it takes width 1, you see. So this is 14, this is 15. Oh, can you see it? Maybe I can increase this. Yeah, so this is 14, this is 15. So so this width is 1. So it goes from 13.5 to 14.5, for example. And The blue dots represent the actual PMF. Okay, with for this distribution. Okay, so it's not symmetric, as you can see, because the P is not 0.5. So you see the numbers kind of match. So 0.02 here, and which is very close to 0, etc. And you see, but it's not exact. You see there's a mismatch here, for example, and here as well. But some numbers seem to match quite well. Okay. Any questions about this? So don't, so maybe one thing I should clarify, don't think of these numbers as sums of Bernoulli P's. I mean, think of this as an independent distribution. Okay, once we defined it, we defined it in whatever way we did, and then this is an honest distribution, and this will come up in its own right. So don't think that you are going to toss so many coins with this heads probability. Okay, this is just an important random variable. This is just an important distribution. Okay. Any questions? Okay, so I will share all this with you later. Okay, so let's do some examples. Okay, so let me do a biology example since some of you are interested in biology, maybe most of you. Okay, so this is apparently some actual thing. So so suppose okay, for simplicity, assume there are two eye colors. Most of us have brown eyes, at least in India. So blue, which could be in other countries, which I'll denote by L, and brown, which I will denote by R. I mean, first letter is common, so you can think that I am using the second letter, or you can think of this as left, right, it doesn't matter. Okay, so it turns out that the eye colors is determined by a pair of genes. Which take values either L or R. Okay. Let's say AB, where A and B belong to the set L or R. Okay, so it's either LL, LR, etc. RL. But R dominates L, i.e., if you have LR or RL, your eye color is R. Okay, so if there's one of each, there's one dominant fellow, which is in this case R. Okay, so only way to get L eyes is LL. Okay, that's the point. So if you have blue eyes, that means both your okay, so I'll come to that. Okay, so yeah, so that means both your genes are L. Is that clear? Okay, so now let's talk about what happens to progeny. So a child receives random gene from each of its parents. So it will get one gene so it will get one gene each from the father and the mother. Okay, so this is a fact. Okay, or the assumption, whatever. Now here is the question. So if the eldest child of two brown-eyed parents has blue eyes, find the probability that exactly 2 of 5 other children, suppose they have total 6 children, have allies. Assume no twins, none of them are twins. And twins complicate the issue because, okay, see why. Okay, so what is the first inference? What can you infer from the first phrase over here, or first clause, whatever?
So each parent has one L allele, like L gene, because the only way that the child can have allies is to have two L genes, and that could be possible only if each of the parent has at least one of the L genes.
Can you say something stronger? Yes, that is correct. So Soham is pointing out that if this eldest child has L eyes, that means, as I said, both genes have to be L, and that means both parents had to have at least one L, right? So everybody agrees with that?
And both have to have exactly one L because the other one has to be R.
Exactly, that's the other part of the confusion, right? But both have R eyes. I mean, that's also given to you. Both parents have brown eyes. So that means that the parents themselves, any of the parents could not have LL, because if they did, then they would have blue eyes. But they are given to be brown eyed. So both of them have one L and one R, right? They have to have one. So by the first clause, both parents have LR pairs. Okay, this is the important conclusion that you have to draw from the first clause. Okay. Now let us talk about. So now we have this information. Now let us try to determine the parameters. So I mean, it's sort of clear from the question that we are talking about some kind of binomial random variable. So we are asking the probability of 2 out of 5 having something. So since this seems like a random variable, it seems like a binomial random variable, we have to determine the parameters. Okay, so it's kind of clear that n is 5 because we are talking about 5. The question involves five other children, and we are talking about 2 having something. So now let's determine the p. So remember that the binomial random variable has 2 parameters, n and p. So let's talk about the first one. Second one. So what is p? So p now is, I mean, from the question, the p that we should look at is the probability of having L eyes, and that is blue eyes. So what's the probability that a child has blue eyes? Blue meaning L eyes. Yeah. What is this?
1 by 4.
1 by 4. Right. So a child will take one random gene from here. Again, the question doesn't say, but you assume that both are equally likely. So you have to take, so for a child to have blue eyes, the probability is of having L comma L, there's only one possibility. So this L can occur in exactly half ways, and this L can also occur in half ways, so we get. So therefore, now, okay, so now we have to answer the question. And here is where we are going to use independence. So it is reasonable to suppose, so assuming independence of eye colors of each child, or no, not eye colors, independence of these genes, that is this AB pairs, assuming independence of these genes for each child, the number having LIs is what kind of random variable? Is binomial with parameters 5 and 1/4, right? Because each child has blue eyes with probability 1/4, and there are 5 children from the question, 5 other children. So this is now a binomial 5 1/4. And this is precisely where we are using the fact that none of them are twins. Because if any one of any two were twins, or they were triplets or whatever, then this independence assumption would fail. So in particular, if they are identical twins, then they will have exactly the same eyes. So if two of the children are identical twins, then they are not independent. They are dependent in the worst way. They are identical, right? So therefore, we have to calculate the probability of x equal to 2. X is equal to this number, and so this is now 5 choose 2, p, which is 1/4 to the 2, and 1 minus p, which is 3/4 to the 3. So one common mistake that people make is forgetting to include this 1 minus p factor. Okay, we want exactly 2 eyes. Sorry, exactly 2 children having blue eyes. Yeah, we of course want exactly 2 eyes. But that means the other 3 children do not have 2 eyes, right? So don't forget to include the 1 minus p factor. I mean, this is a common mistake. So here, don't forget to include this. Okay. If you forget to include this, that means you are saying that there are at least 2 eyes, at least 2 blue eyes. Okay. Okay. So 5 choose 2 is 10, and then I have 3 cubed, which is 27, and divided by what? 4 to the 10 times 2, which is 2 to the 11, and 1 2 will cancel. So this is 27 times 5, which is 135, by 2 to the 10, which since you have all done a computer class, will know that this is 1024. Okay, so it's about 13%. So yeah, so it's a fairly small number, as you should expect, because each child has probability 1/4, so which is a small number, and so So having 2 out of 5 children both having blue eyes is a big deal. Okay. Okay, is the example clear? Okay. Okay, let's do one more example. No. Okay. So let's suppose there is a system which has n components. Each of which fails with probability 1 minus p. That is, it works with probability p. So the system functions if at least half the components function. Half the components work. Okay, so there are some redundant components, but this is this is not uncommon. I mean, so one often keeps fail safes in case something malfunctions. Okay, now the question is the following. So for what values of p is a 5 component system better than 3 component? Okay, so let us define our 2 random variables carefully. So is the question clear? So so you have to there are n components. We are looking at n equal to 5 and n equal to 3, and the failure rate is or whatever failure probability is from SP. And when is the 5 component system better? So you have to interpret what better means. Okay, so what do you think better means? Okay, so maybe someone can answer.
So the probability that the system works should be more.
Yeah, exactly. So you cannot say better in any deterministic sense, at least as far as this question goes, but we can say probabilistically. So in the long run, which should work better in the sense which functions for longer time or some such thing. Okay. So let's define our random variables. So let x1 be the random variable for the 5 component system. So what kind of random variable is x1?
So binomial random variable.
But with what parameters?
5 comma p.
Right. So okay, so that's good. So we take p to be the success rate because we want to talk about functioning. So we want to say that it works. So the probability of it of the system functioning, right? So we want to say that the component does not fail or works properly. So we will use the parameters p for the success probability, right? Which is the natural one. And similarly, x2 is a binomial random variable, again with three components, and therefore n is 3 and the same p. Okay. So now what do we want to calculate? So the first thing we want to calculate, let's say part A, is the probability that the 5 component system functions. What is this equal to in terms of x1? What is this equal to?
So it's the probability that x1 is equal to 3, x1 is equal to 4, plus probability that x1 equal to 4 and plus
Yeah, can you
probability
say it compactly? That's right.
5 choose 3.
No. What? Just a single expression here in terms of x. x1 is greater than or equal to 3. Right? I mean, you are saying x1 equals 3 plus x1 equals 4 plus x1 equal to 5, which is the same as it. Right. But it of course amounts to the same thing. So this is the sum I equal to 3 to 5. 5 choose I, p to the I, 1 minus p to the 5 minus I. Okay? So now let's expand this. So what is 5 choose 3? That is 10. P cubed, 1 minus p squared. What is 5 choose 4? That is 5. P to the 4, 1 minus p to the 1. So I'm not writing the 1. Plus 5 choose 5, which is 1. P to the 5, 1 minus p to the 0. So I'm not writing this. Okay? Okay, now let's, I'll use my modern technology to make my life easy. So what is the probability that the 3-component system functions? Now what's the, so this is something involving x2, and now this is x2. I mean, if x2 is 1, that's not okay, because we want at least half. So it should be more than 3 by 2. And so 3 by 2 is 1.5, and this x2 takes integer values, again same kind of argument. So x2 has at least 2. And so this is sum I equals 2 to 3. 3 choose I, p to the I, 1 minus p to the 3 minus I. And so now this is 3, first term is 3 choose 2, which is 3. P squared, 1 minus p to the 1, I'm not writing the 1. Plus 3 choose 3, which is 1, I'm not writing that. P cubed, 1 minus p to the 0. Okay? Alright. So, okay. So now we want to compute a minus b. So a minus b is equal to what? So we want to say that this probability is greater than or equal to 0. Okay. So want to find p such that a minus b is greater than or equal to 0, or greater than 0, whatever. So a minus b now is equal to what? So I have, so let me write the first two terms. So that's 10p cubed 1 minus p whole squared plus 5p to the 4 1 minus p. I'll write the last term later. Let me write this difference over here, minus 3p squared 1 minus p. And now let me write the last term from here and the last term from here. So plus p to the 5 minus p cubed. And the reason I'm doing this because I want to take some common terms to simplify my life. And this is now exactly p cubed times p squared minus 1. Okay, now if you look at all these terms, I have p cubed here, p4 here, p squared here, and p cubed here. So p squared is common. I can take it outside. And I have 1 minus p whole squared, 1 minus p, 1 minus p, and p squared minus 1 factors. So there's a 1 minus p factor here as well. So 1 minus p I will take common. Okay, so now what do I get? From the first term I get a 10p, 1 minus p. From the second term I'll get a 5p squared. From the third term I'll just get a minus 3. And from the last term I will get So here I have to be careful about the sign. So I'll get minus p, oh sorry, plus, no, I should take a minus because p squared minus 1 is p minus 1 into p plus 1, but I'm taking 1 minus p, so I get a sign, and the remaining factor is a 1 plus p. Okay? And now let me collect common terms. So let me take the p squared term. So I have a minus 10p squared here, plus 5p squared, and a minus p squared. So that's minus 11 plus 5p squared. So that's minus 6p squared. So I have collected this, and this term. Now let's look at the p terms. I have 10 to the 10p, sorry, and I have minus p. So I have a plus 9p, and I have taken care of this and this term. And now the only term remaining is 3. So now this, so you notice that 3 is a common factor, and there are unnecessary minus signs. So I'll take minus 3p outside. Sorry, minus 3 outside, so I get minus 3p squared 1 minus p, and I'll write this as 1 minus 2p, sorry, 1 minus 3p plus 2p squared, which as you all know factors into 1 minus p into 1 minus 2p. So I will write this, so now I'll absorb this minus sign over here, so I get 3p squared. Because I'm dealing with inequalities, I don't want extra negative signs hanging around. So 3p squared 1 minus p whole squared times 2p minus 1. Okay. So fortunately everything factors nicely, and we want this to be greater than or equal to 0. Right? That's what we said. A minus b should be greater than or equal to 0. Okay. And what's nice about this is that these guys are positive. Okay, so again the question doesn't say it, but it should be clear that the question makes no sense if p is 0 or 1. Right? If p is 0 or 1, what are we talking about? The system always fails or always functions, so there's nothing to talk about. And in real life it never happens anyway. So this part is positive, so we want 2p minus 1 to be positive. Okay, let's okay. So we want p to be greater than or equal to 1. Okay. So we have a fairly clean answer. I mean, it was not clear from this complicated looking formulas that it will work out nicely, but it does. And as an exercise, show that for any k, for any n, the 2n plus 1 system works better than the 2n minus 1 system. So in other words, the same question as above. I mean, this is where n is more general. Here n was 2, now it's n is arbitrary if p is greater than or equal to 2. So again the same condition. So you can show that you get the same. I mean, so the same condition works in for general n. Okay. Any questions about this?
Sir, if instead we would have said that the probability of a 5-component system working is 5c, if I choose 3 into probability, I mean into p cube, wouldn't that be sufficient? Like, what is the mistake in approaching the question like that?
So wait, so you're saying, so but that so let's check. So you are saying that this probability should just be 10p cubed?
Sir, like the probability of a 5-component system functioning would be just choosing any 3 out of the 5 and ensuring that they work, irrespective of what happens to the other 2. The system would work.
That's right.
No, but
That's
I
right.
think there would be overcounting by doing like that.
Why?
Sir, because I mean, for example, let's say the components 1, 2, 3, 4 work,
Yes.
and 5 does not work. So
Yes.
we are counting this case in a lot of different ways. The same case we are counting in a lot of different ways. Like first we chose that 2, 3, and 4 will work, and then we choose 1 and 5 in any way we want. Even there we are counting it once, and we are also counting it in the situations where 1, 2, 3 work and 4 or 5 are free to do whatever they want.
Yeah,
So
that's
there's a
right.
lot of overcounting going on.
Yeah, so just to check, we can expand this out. Let's expand this one out. So I get 3p squared minus 3p cubed plus p cubed, right? So if Soham, if your argument was correct, this would just be 3p squared, but it's not, because this is 3p squared minus 3p cubed plus p cubed, so that's minus 2p cubed, right? And so again, we could expand this out and check. So you will certainly get 10p cubed, but you have to subtract something off. So exactly as Prithu said, I mean, you can do that by some kind of inclusion exclusion, and you will get the other factors. So maybe, so we have 10p cubed over here, and so you'll have 20p to the 4 minus 20p to the 4 plus 5p to the 4, so that's minus 15p to the 4, and you'll have 10p to the 5 minus 5p to the 5 plus 1p to the 5. So that's plus 6p. You can see the Pascal's triangle kind of things.
Yes, sir, got it.
Right. Okay. Maybe this is a good time to stop. I'll start a new distribution. I could maybe define it now, but I think it's better to start in a new class. Okay. So I'll stop now, and I'll see you next week.
Excuse me, sir.
Yes, Anirudh.
Like if you would have started like 1 minus p to the power x less than, like instead of going this way.
Yes, that's right. But it doesn't. Yeah, that's right. That's right. So, good point. So, Anirudh's point is, if I had taken the complementary events, so I had instead taken 0 to 2 here, and had taken 0 to 1 here. But unfortunately for you, the number of terms is the same. And this is because it's odd. And we are taking exactly half. Right? So there also you would have 3 terms. And in fact, it would be more cumbersome because the 1 minus p powers would be higher. So actually this is better.
Okay, sir.
Yeah. But that's the right way to think. You should certainly think like that, because in questions, if I had given you 3/4 of the, if I had replaced half by 3/4, then it would certainly benefit you to do the other calculation, because this, no, sorry, if I had done 1/4, then here there would be many more terms compared to the complementary terms. Yes, but please do think like that. Yes, exactly. Good point. Okay, if there are no more questions, I'll stop. Okay, all right. See you next week then.